I don't have the previous soft copy of the notes from our previous classes because I'm using a different computer and a different application for writing. So, do you remember the statement? So, we were looking at a function f from Rm to Rn, right? And P was a point in Rm. What were we looking at? We want the derivative, which is dfp, or alternately f prime p. We want this thing to exist, right? Right? What does that mean? It means this linear map to exist, right? Linear map from Rnp to Rmfp to exist. So, okay, he has left, it seems. So, anyway, so we want this thing to exist, and what was the sufficient condition for that to exist? The sufficient condition was that first we can reduce it to a function from Rn to R1, and we can say that if for a function, if for a function like this, dfp, which is or f prime p, exists from Rnp to R1 fp, if this matrix, which Rudin writes like it is an element in L of Rn R1, right? That is how Rudin writes it. That this f prime p is an element here. Here, the only extra thing we are adding is Rnp and R1fp. This index we're tracking. Anyway, so we are finding a sufficient condition for this thing to exist, and what was that? That was the partial derivatives del f, or del f del x1, del f del x2, del f del xn. These partial derivatives at the point P to exist and be continuous, right? Exists and continuous. We had mentioned that Apostol makes some distinction that not all of them have to be continuous at that point. At least one can be not continuous, but Rudin doesn't make any such distinction, right? Because we are finding a sufficient condition. In this case, you are taking at least a little more assumption. That's fine. So the boundary situation is you can do away with the continuity of one of these derivatives to show that this function is actually in a continuously differentiable function category. So anyway, what was the proof that we outlined in the last class? So what was the statement? The statement was, actually I've written it a little odd way. I better have written that if for f from this, the partial derivatives. These exist and are continuous at p, then f is differentiable at t. Right? That was the statement. And what was the outline that we did? What was the outline that we did?
We used the telescoping technique.
Yes. So what was that? So what do we have to show finally? For f being differentiable at p, we have to show that if dfp, let's stick to this notation dfp. If dfp is the map from Rnp to R1fp, then that is the derivative that we suggest. Then this to exist, we have to show that f at p plus h minus f at p, then that is what? dfp of h plus some error term which is at the point p and which depends on the value of h. And what can we say about this error term? That this goes to 0 as h goes to 0. Right? We have to show that. And here, this is a real number, this is a real number. So all these are real numbers. But what is this? This is in Rn. Where is this? This is in Rn. H is in Rn. So these things are in Rn. These are real values. So we have to show that the difference between this and this is an error which goes to 0 as h tends to 0. How do we show that? We need to find a sufficient condition. What did we say? That these things existing is a sufficient condition. Existing and being continuous is a sufficient condition. So how does that make sense? Just tell this much, then we will be done. Okay? How do we do that? Moitro, you said you have seen the proof. Can you recall?
Yes, sir. We have to break down the series into some terms and then take the sum.
Yes, but how does it work? How did we break up in the last class? Bitan, can you recall? How was it done? Are you present? How do we do that? Please recall. Otherwise, it will be like I'm talking to a wall. How do we do that?
So I think we have to write the df, ph in terms of df, p minus 1h and
P minus 1h? What is P minus 1h? See, this is something not very difficult, and we repeated. This is the third time I am repeating this. I had told you even in terms of pictures that I want to go from this point to that point. Suppose I have a map in R2. Last time I had described it in terms of R2 functions. This is my point P, this is the point P plus H. I need to go from this point to that point. So what is the difference between this point and that point? There is H, right? So then which vector is this? Which vector is this? Which vector is this?
So this is the H vector.
This is the H vector. Very good.
Yes.
So this is the vector P. Suppose this is the origin. This is P and this is H. Now, how did we say that? What did we do? We wrote H as H1, H2, Hn, right? And then what did we do? What did we do? We wrote P plus H as, see, H1, H2, Hn means I can write this vector as H1, E1.
E1 plus the H2 of Hn.
E2, Hn, En, right? So P plus H is just like P plus H1, E1 plus H2, E2 to Hn, En,
Yes.
right?
Yes. Yes.
Now, what I can do is, I can, suppose I have to, now I have to express this difference, right? F of P plus H minus F of P. What I was doing there is, I was writing this, I have to go from P to the point P plus H, and P plus H looks like this. So what I was doing is, from P I was first going to P plus H1 E1. Then from that point P plus H1 E1, call that P1, I was going to P plus H1 E1 plus H2 E2, call that P2. So P0 being the point P, P1 being P plus H1 E1, P2 being P plus H1 E1 plus H2 E2. This way, P plus Pn will be the point P plus H, right? That will be P plus H1 E1 plus H2 E2 plus Hn. That will be P plus H. So I will go from P to P plus H, but in n steps. Okay. So how will I do that? So I will do it like, suppose then I'll write these points as P0 is P, P1 is P plus H1 E1, P2 is P plus H1 E1 plus H2 E2. This is clear, right? These expressions. So this way, Pn would be the point, P plus H, P plus summation Hi I from 1 to n, and that is P plus H, right? Right? So P0 would be P and Pn would be P plus H. So I can write this as Pn minus, I'm not writing f of P0 right away. What I'm writing is f Pn minus 1 plus f Pn minus 1 minus f Pn minus 2 plus now you understand, right, what's going on here. So this way, where will it end? Where will it end? F of P2
P1.
F of P1
P1
plus F of P1 minus F of P0. Right?
P0, P0.
Now you see in this sum, this thing cancels with this. So all these terms are getting cancelled in this, right? right? This with the previous term. Similarly, this with the previous term, this with this, right? So all these terms are getting cancelled in this sum,
Yes.
right? What remains is this term
FPN minus
and
FP0.
this term. And what is that? FPN. Pn is p plus h. That is f of p plus h minus, not this minus, this minus f of p naught. What is p naught? P naught is p. So the final thing is f of p plus h minus f of p. So nothing has changed. I have just written this difference as a more elaborate difference, sum of smaller differences. What do I achieve by writing this difference in this way? If you look at the first difference, what is it? It is f of p plus, okay, let me not write the first thing first. So, okay, I can write it as Pn is what? Pn is p plus summation hi from 1 to n. So I can write that as summation I from 1 to n minus 1 HIEI plus HNEN, right? I can write it that way, right? So what is this? How do I know this element? This is
P of n minus 1.
Pn minus 1, right? Minus, what did I have? F of Pn minus 1,
Yes.
right? So this difference, I have so many other terms. I have not just focus on the first term first. So what I have is f of Pn minus 1 plus Hnen. So this is Pn minus 1. So Pn minus 1 plus Hnen minus f of Pn minus 1, right? This difference plus everything else. I'm not going into that right now. Okay? Do you understand this? Bitan and Asif, I am asking. Are you people present? Are you people present? Bitan, Sharkar and
Yes,
Asif,
sir.
Iqbal?
Yes, sir.
Yeah, so do you understand what I have written? Is that clear? See, you asked me to repeat it. I'm repeating. So you have to interact. I mean, if you are following it or not, where you have any problem, you must have asked me to repeat it because you had some problems. So you have to tell me if you're following or not. Do you follow
Yes, sir.
till this
Yes, sir.
point? Okay. Do you have any question?
No, sir.
Okay. So can you tell me now, how can I simplify this? Does it look like something? What is it? I have to reach this point, right? Where I can say f of p plus h minus f of p is this linear function. Now what is DFP? I know what DFP is, right? DFP is this del f del x1 at p del f del xn at p. That is DFP, right?
Yes, sir.
Right? So I have to reach this difference, but I have not yet done that. What do I have here? Pn is a point in the domain. So if the domain is this, if the point P is this, and say this is P plus H, then what is this point? Pn minus 1. Suppose Pn minus 1 is this point. Okay, this point is Pn minus 1. So what is this point? This is P plus H, that means this point. How do I write that? Pn minus 1. Okay, suppose I'll change this. I'll write Pn minus 1 here. Suppose Pn minus 1 is this point. So from P I have reached Pn minus 1. I have added Hn En, and that point is P plus H. Then this is the vector, right? Hn En. This is the vector Hn En. So Pn minus 1 plus Hn En is P plus H. So I'm looking at this difference. F at P plus H, which is this is P plus H. And F at Pn minus 1, which is this, right? So I have to look at this difference in the functional value. What does that mean? You are looking at the difference of the function in the nth coordinate direction. Yes or no?
Yes.
Right? So what does that mean? Does it ring some bell? I'm looking at the difference. Call that point Pn minus 1 x. Suppose I call this point x. Then what does the difference look like? X plus Hn En minus f x. What does this look like? Is it not the difference that you had looked at for the directional derivative in the En direction? Is this not the difference you had looked at in the directional derivative in En direction? What was the
It's exactly that.
definition?
F
Limit
of x plus
Hn goes to 0, this difference divided by Hn. That was the
Hn.
directional derivative in En direction, right? Right? So x, f prime x at En direction, that was the definition. So if I remove these things,
Sir, just one small interest, sorry, just one student is trying to join. Can you please let me know?
oh, okay.
He was late, we were having class.
Yes, sure.
Okay, thank you.
I have
Yes, sir. He has joined.
Okay. So, what does it look like? Wait a minute. Some two things are working. So I have the computer mouse and the writing tablet, so both are working together. Okay, so now I think it's fine. So this is what we had as the definition of a directional derivative at the point x in the En direction, right? Now if I know, so tell me, how do I usually write this thing? What is the usual way of describing this? That is del f del xn at the point small x, right? Yes or no? The directional derivative in the nth coordinate direction is the partial derivative with xn coordinate.
Yes, exactly. Yes.
So I know the partial derivative exists, right? And also that it is continuous. Yes or no? I know the partial derivative exists and it is continuous, right? So I can measure this difference. I can approximate that with the partial derivative and some bit of error, right? So this difference would be the partial derivative, which is what? This at the point x, right? And hn. Now see, this is a number and hn is a number, right? Plus some error, right? And that error
Yes.
goes to 0 as hn goes to 0. Yes or no? This is what we know because the partial derivative exists. Partial derivative for a real valued function, then everything is boiling down to a one variable situation, right? This is a number. I'm applying that on hn in this case. I had f of p plus tv minus f of p, where limit t was tending to 0 divided by t. Here hn is playing the role of t and x is playing the role of p, right? And that was f prime at p in the direction v. So this is f prime at the point x in the direction en, and that is called partial derivative del f del x n at the point small x. You can call it y also if you like to, because too many x's are floating around. So anyway, that doesn't matter. So del f del x n at the point small x, which is a real number acting on h. So this is a real number with which you are approximating this difference, which is also a real number, plus some error which goes to 0 as hn goes to 0. Is it clear to all of you?
Yes.
So if I break up this difference as this sum of smaller differences, then I observe that this first difference can be written as Pn can be written as Pn minus 1 plus Hn En minus f of Pn minus 1. And that quantity can be approximated by del f del xn, right? Plus some error. Do you agree to this much? Only this first difference can be approximated by del f del xn on hn, where you have some error term, but that error term goes to 0 as hn goes to 0. Do you agree to that much? By this, I take care of this first difference. Okay?
Yes, sir. Yes, sir.
Fine. Now I can do the same thing with the second difference, right? So I don't have to write here. Now for your benefit, I had written x here so that you understand this. Now I can replace it with Pn minus 1, right? Pn minus 1 plus Hn, and this is Pn minus 1. And this point also I can go back to Pn minus 1. Okay? So this thing is Pn minus 1. Now there is a one very important observation at this point. You see the derivative is taken at the point Pn minus 1. This is the partial derivative at the point Pn minus 1. You understand that? We had assumed that the partial derivatives exist at the point P, right? And is continuous at P.
Yeah.
It exists in the domain and it is continuous at point P. Right?
Yes.
Right? So, how does the continuity help me now? Can anyone tell me? Because finally I have to go to the partial derivative at the point P. Here I am not getting the partial derivative at the point P, I am getting the partial derivative at the point Pn minus 1. Keep this question in mind, I am coming back to it in a moment. But if I go to the next line after this, I can see that this difference, f of Pn minus 1, so this was the first difference. Now the second difference I can write as f of p, what was it? Pn minus 1 minus f of Pn minus 2. So this was Pn minus 1 minus f of Pn minus 2. Now, what can I write for Pn minus 1? Just like I had written, this was my Pn. For Pn, I had written Pn minus 1 plus Hn En. What can I write for this? Anyone, please? What should I write here? What should I write here? Very similar to this.
Sir, del f del x n, del f del x n minus 1 at Pn minus 2.
No, I'm not asking for the right hand side. I'll come to that later. I'm asking the argument in this thing.
Oh, sorry.
What should I write within the bracket here?
Pn minus 2 plus Hn minus
Right.
1, En minus 1.
Right. So Pn minus 2 plus Hn minus 1, En minus 1. Right? So now again you call this point x and that point x. So this will be f of x plus Hn minus 1, En minus 1 minus f of x. What does that mean? That means del f del, which direction it is varying? En minus 1. So del f del xn at the point x on Hn minus 1 plus some error term, right? Which goes to 0 as Hn minus 1 goes to 0. Yes or no?
Sir, it's still del f del x n. It's the xn.
Sorry. Yes, it's xn minus 1. Wait a minute. Yes. This is xn minus 1. So what point should I write here? At which point?
Pn minus 2.
Pn minus 2. So it is del f del xn minus 1 at the point Pn minus 2, which is also a real number again, multiplied with Hn minus 1 plus some error. So the second difference here, I am approximating that with this. Okay? Clear? At least this much is clear, right?
Yes, sir.
Now, if I add 1 and 2, what do I get? What do I get if I add 1 and 2? This term gets cancelled, right? These two terms are getting cancelled, minus fpn minus 1 and fpn minus 1. This is pn minus 1, right? So this and that same terms are getting cancelled. So if I add the two equations, what I get is fpn minus fpn minus 2 is del f del xn at the point Pn minus 1 acting on Hn plus del f del xn minus 1 at the point Pn minus 2 acting on Hn minus 1 plus some error term which is the sum of these two errors. Yes or no?
Yes, sir.
Yes? Very good. Now, you understand, I will be getting similar equations for all these differences. Right? Right?
Yes, sir.
For all these differences, I'll be getting similar terms.
Yes, sir.
So this was the first difference, and this will be the nth difference. So I call it, or nth difference. I call it n. Okay. What will be that? It will be f of p1 minus f of p naught, right? And I can write, what should I write in place of p1? Just like this. What should I write in place of P1? Something minus f of P naught. This is P1. What should I write here? What should I write here?
Sir,
P naught plus
P0 plus, yes sir, P0 plus
E1.
H1 E1, yes sir.
Right? Yes. So again, I can write this as del f. I can approximate this left-hand side difference by del f del x1, right? Because in the E1 direction, this is a derivative in the E1 direction. At the point P, which point? E
So P naught.
naught, right? P naught will be evaluated on H1. That means will be multiplied to H1 plus some error term which goes to 0 as H1 goes to 0. Correct?
Yes sir.
Yes, sir.
So if I add all these equations, you see this term is cancelling with this term. This term is cancelling with the next equation, first term. Similarly, this term is getting cancelled with the previous equation, last term, right? What remains is f of Pn minus f of P naught on the left hand side. If you sum all of them, right, what you get is f of Pn minus f of P naught, correct?
Yes sir.
And that is, so that is f of Pn is what? E plus H, that is Pn. Remember, Pn is P plus H.
Yes, yes, yes. Yeah.
Minus Fp naught. What is that? What is P naught? P naught is P. Right? So f of P plus H minus f of P, that is f of Pn minus f of P naught. And that we get by summing all the right hand sides of these equations. What is that? It is del f1 del f del x1 at P naught on H1 plus del f del x2 at P1 at P1 on H2, okay, plus del f del x3 at P2 acting on H3, right, and so on, plus del f del xn at Pn minus 1 acting on Hn, right? Right? This entire thing plus the sum of all these errors, this error, this error, this error. So sum of all those errors, right?
Yes sir.
That I am writing, suppose epsilon at the point P on H. I'm not writing H. Here you saw that the first thing goes to 0 as Hn goes to 0. The second thing goes to 0 as Hn minus 1 goes to 0. The last thing goes to 0 as H1 goes to 0. Right? So all these errors, I'm clubbing them together and calling them epsilon P on H. Okay? Now you see what happens as H goes to 0. As H goes to 0, what happens? H goes to 0 implies H1, H2, Hn, that goes to 0. That goes to 0 means all of them go to 0 individually. Yes or no? H going to 0 means all of them going to 0 individually. And H1 going to 0 gives you this error going to 0. H2 going to 0 gives you the previous error going to 0. Similarly, Hn minus 1 going to 0 gives you this error going to 0. Hn going to 0 gives you the first error going to 0. That means if H goes to 0, cumulatively, the entire error goes to 0 because all of them go to 0 individually. So their sum will also go to 0. Yes or no? Yes or no?
Yes, sir. The total error will go to 0. Yes, sir.
Right? The total error will go to 0. What else is happening? That is important. So now I understand that as h goes to 0, this total error will be going to 0. So the difference of the function value will be the sum of these things, right? But is that all, or something else is also happening? Can you see anything else happening here? That's very important. H going to 0 implies HI's are going to 0 individually, but what does that imply in this expression? Does
Sir,
anything?
those partial differential terms,
Yes,
their HI is also going to 0, right?
yes, very good.
So,
They are going to 0.
Can we kind of say that that all the different P points are going to P naught?
Yes, very good. So P naught is P, right? So P1 was what? P1 was P naught plus H1 E1?
Yes.
Or what this P naught P1 yes, P1 was P naught plus H1 E1. Since H1 is going to 0, H1 E1 is going to 0 as well. That means P naught plus H1 E1 is also going to P naught, which is P. That means P1 is going to P. So if H goes to 0, HI's are going to 0 individually. That means, that implies HI goes to 0 for all I. That implies PI goes to P naught, which is P for all I. Right? Right? Or you may say Pi minus 1 goes to P naught for all I. Right? That means all these points are coming to P naught, which is P. But there is a question here. Which question? Can you tell me what is the question here that still remains? We had got del f del x1 at P naught, that is fine, but del f del x2 at P1. We don't want to approximate the left hand side with del f del x1 at P naught, but del f del x2 at P1, del f del x3 at P2, del f del xn at Pn minus 1, and all those terms, right? Do I want these terms? No. What do I want in these places? I want a df dx del f del x del f del x2 at the point P naught. I want a del f del x3 at the point P naught. I want a del f del xn at the point P naught. Yes or no? Yes. So what happens if I replace this term by a del f del x2 at P, del f del x3 at P, del f del xn at P? What happens?
So we get the gradient.
We get, but in addition, we are getting also something else. What is
Yes,
that?
sir. We get a gradient dotted with H1, H2 till Hn.
Yes, but something more than that. See, this error we know it vanishes as H vanishes. But here we haven't got the gradient yet. We got instead del f del x2 at P1, del f del x3 at P2, del f del xn at Pn minus 1. So in order to get gradient at the point P, we want this term to be del f del x2 at P naught, del f del x3 at P naught, del f del xn at P naught. So suppose I replace these terms by the desired terms, del f del x2 at P naught, del f del x3 at P naught, del f del xn at P naught. What happens? Remember, h is going to 0. That means hi's are going to 0.
Yes, sir.
What does that
So
mean?
basically, the expression of the dotted expression becomes 0 because the HI is also go to 0.
Yes, but before that, you are replacing this term. Okay, I'll go to the next page. Just a moment. See, so I have on the left hand side f of p plus h minus f of p, which is this summation, right? So in that summation, I have one error term which is going to 0 as h is going to 0. That much I am convinced of, right? So I have a summation like this. But in this summation, the derivative terms, the partial derivative terms that appear, are at different points. They are not at the same point, right? Suppose I make them all at the same point. Del f del x1 was all right. It was at p, which is p naught, at h1, plus suppose I write del f del x2 at p again on h2. Suppose I write del f del x3 at p again on h3 plus del f del x4 at p on h4 plus this way, you understand, plus del f del xn at p on hn, right?
Yes, sir.
Okay, this entire thing plus this error, okay, where I know that this term is vanishing as h is vanishing. Remember, h is anyway vanishing. We have assumed that. There is no problem about that. But look at the difference between these two expressions. Here, there was del f del x2 at p1. I have written del f del x2 at p naught. Here it was del f del x3 at p2. I have written del f del x3 at p naught. Del f del x3 at p4. I have written del f del x3 at p naught. So all these pi's or pi minus 1s, I have changed them to p or p naught. So shouldn't that gather some errors? Because this was a different term, right?
Yes, sir.
This
The
is a
errors
different-
that we gather will go to 0, right? Because the h is
Why?
actually going to 0.
Sorry? Yeah, why is that going to 0?
Because the h's are also going to 0. Because h is going to 0.
Yeah, so what makes the error to go to 0? It is not necessary that if hi goes to 0, the error should also go to 0, right? The error is between what? What are the two things that you have the error between? The difference is between what? It is between del f del x I, del f del x I at the point pi minus 1 on h I minus del f del xi at the point p naught hi. Right? That is the difference.
Yes, sir.
Now, why do I expect that this difference is going to 0 as hi is going to 0?
Second, because I think the point pi minus 1 will tend to p naught.
Yes, the point pi minus 1 is tending to p naught. But why is that? Why is the difference between these two things is going to 0 in that case? There is an assumption which facilitates that. We are forgetting that assumption. What is it?
So that f is continuous.
No, we are not using the continuity of f here. Look at it well. Continuity of something should give me that. But continuity of what?
Sir, the continuity of del f del xi.
Del f,
Yes.
del f del x, yeah.
Continuity of del f del xi is telling me because pi is going to p naught, del f del x I at p I minus 1, since the I minus 1 is going to p naught, the del f del x I at p I minus 1 should go to del f del x I at p naught, right? What is continuity? X going to C, fx going to fc,
FC, yeah.
right? So here pi minus 1 going to p naught, del f del xi at pi minus 1 going to del f del xi at p naught. That is the continuity of del f del xi that we are using here, right? That means this difference is an error, right? If you
Yes.
see that I have left a little bit of space here, so here too I am gathering some error. Let me call that E2. Here is E1, but E1 is 0 in any case because P0 is P. So I don't need to do anything here. That is why, that is the reason Apostle had said that we need continuity for all but one. You understand now? Apostle's statements say that the function will be differentiable at that point if all the partial derivatives are existing and all of them are continuous except one. At least, I mean, one you can do away with. Why? Because of this reason, that here you are not gathering an error because you are not changing anything. This is P naught, which is P itself. So you don't need to do anything here. Here you need to do something. That's why you are gathering some error. E2, I call it here. You're having some error here as well. E3, I call it. So on. E4, let's call that. Plus E, this is 4, so this is En. Okay. Now what can we say? From the continuity of these partial derivatives, all these errors, E2, E3, E4, En, all of them are going to 0. So E2, E3, En are all going to 0 as H is going to 0. Because H is going to 0 implies HIs are going to 0, HIs are going to 0 implies PIs are going to P0. And that combined with the fact that the partial derivatives are continuous at the point P, these points are approaching P, so the partial derivatives at these points should also approach partial derivatives at the point P. Okay? That is why I can replace these terms, these partial derivatives at different points by partial derivatives at the point P. What will be the effect? If I change it to this, I'll accrue some error, right? But all these errors are going to 0 individually, and the sum will also go to 0 individually, finitely many of them. So the sum is also going to 0, right? Is it clear to all of you?
Yes, sir.
Yes, yeah.
Okay, so then finally, you can also remove all these errors and club them together with this error and call it maybe epsilon hat or whatever. And you see that big error, that cumulative error, epsilon hat at the point P goes to 0 as H goes to 0, which we have just now explained. What remains? Remains is del f del x1 P on H1 plus del f del x2 at P on H2 plus del f del x3 at P on H3 and so on. Right? So from this equation, I can write del f del x1 at P on H1 plus del f del x2 at P. Remember this base points P that is coming from the continuities. Del f del x3 at P on H3 plus so on del f del xn at P on Hn. This entire thing plus some big error which I am calling epsilon hat at the point P on H. And what do I say? I am saying that this is going to 0 as H goes to 0. Clear? So f of p plus h minus fp is this thing, right? Plus some error which goes to 0 as h goes to 0. Now what is this? What is this? What can I say about this?
So the first term is a gradient dot h1 h2 h3.
Yes, so this is del f del x1 at p, comma del f del x2 at p up to del f del xn at p dot the column vector h1, h2 and so on up to hn, right? Right? Plus this error term, which goes to 0. Now this is the definition of derivative for this function f, right? Is that not the definition? This is the definition, right? This thing. This dfp is what? Dfp is this gradient. See here? This is the gradient. Exactly, that is what I'm getting. This is dfp, right? And dfp on h. H is in Rn, right? That means h is what? H1, H2, Hn. I'm applying dfp on H1, H2, Hn. What do I get? It's a matrix, right? DFP is a 1 by n matrix. That means a row matrix, this thing, which we call the gradient. Apply that on an n vector. That means n by 1 matrix. So 1 by n times n by 1 gives you a 1 by 1 matrix, which is this sum, which is the inner product or the dot product, you can say. Right? That shows you the derivative exists. It follows the definition. The error vanishes. Right? So, if this is differentiable at p, correct? F is differentiable at p. So this is a sufficient condition, right?
Yes, sir.
Yes, sir. Yes.
Okay, now if I tell you I have a function like this, what will be the sufficient condition? Can I say the same thing?
So we will need an m into a matrix.
Yes, but in that case, that was our goal, right? Our goal
Yes.
was not to find a sufficient condition for differentiability of a function f, which was defined on Rn to R1. That was not our goal. Our goal was to find a sufficient condition for differentiability at p for a function from Rn to Rm. Now that we have found a condition, a sufficient condition for functions from Rn to R1, what should be the right condition for functions from Rn to Rm? Do you understand my question?
Yes, sir. I think what we could do is similar to the above expression, except the gradient matrix will be at each point P1, where the Pi are components of P.
Yes. Not exactly. PIs are components of P in our previous notation. If you follow the notation, PIs were successive points towards P. If I take a broken path from P to, so it's like this, that this is your Pn minus 2. This is your Pn minus 3. You understand?
Yes,
This is again your Pn minus 4 and so on. You are so this is your P, which is P naught. This is your P1, which is P naught plus H1 E1. This is P2, which is similarly defined, and so on. So with a broken path, zigzag path like this, you are going from the point P to P plus H. What we did is we exploited this expression for H, which is H1, Hi plus Ei, summation Hi plus Ei. We exploited that expression. We restricted it part by part using this telescoping sum and saw that each of those differences are approximated by the partial derivatives, right? If the partial derivatives exist, we have seen that these differences can be approximated, right? So that is how we got the sufficient condition for the function from Rn to R1. Question now, which is not a which is not a very difficult question to answer. That what do we do for Rn to Rm? I guess you already know the answer. We're just not able to relate, see what is being asked, probably.
so is it DFP into the H1 vector?
No, can you tell me what question have I asked? Which answer am I looking for?
So are you asking about the final form of the final expression, like
No,
FP plus
I'm
H?
asking for so here the here the sufficient condition was for a function like this. I said if for a function like this, all the partial derivatives exist and the function is continuous at the point P, then the function is differentiable at P. Okay? Is that correct? We understood the proof?
Yes, sir.
Now I'm asking what will happen, what will be the sufficient condition if I replace 1 by m? If I put Rm here, this condition is not enough. That we understand, right? Right? So which conditions should I take? That is my question. In that case. Very easy. Should be able to answer it immediately.
Sir, in the first case, we said that the partial derivatives exist and f is continuous, right?
Yes.
So
Partial derivatives they exist and not f is continuous. All of the partial derivatives are continuous. See, we haven't used the continuity of f, but we use the
Yes, sir.
continuity of the partial derivatives at this point.
yes, sir, yes, sir.
Yeah. So partial derivatives should exist and should be continuous at the point. And in fact, we can do away with continuity of one partial derivative, but no need to be so specific. We assume all of their continuity. So what should be the right condition here? See, here we have taken partial derivatives of real valued functions. If I have Rm here, I will be having a vector valued function from defined on Rm. Right?
Yes, sir. So we should take the individual components, right?
Even that is not required. That will follow immediately, but we will take partial derivatives of vector valued function. We also know that, right?
Yes, sir.
If I have a function like this, I have seen the definition of f prime p in the direction v. What is that? That is limit t tending to 0, f of p plus t v minus f of p, right, over t. That was the definition for the directional derivative at the point P in the direction V. Yes or no? Now you see that del f del xi at the point P is nothing but f prime P ei. Right? Yes or no?
Yes, sir.
And what is that? Limit t tending to 0, f of p plus t ei minus f of p over t. Right? Yes or no?
Yes, sir. Yes, sir.
Here f is a Rm valued function. So this is an Rm vector, this is an Rm vector. We have talked about all these things earlier. The difference between Rm vectors is an Rm vector divided by t is still an Rm vector. Limit of an Rm vector is an Rm vector. So this thing is a vector in Rm. So what am I referring to when I am talking about partial derivative of this kind of a function f? What am I referring to in the matrix? The matrix, derivative matrix is a m by n matrix, right? So m rows and n columns. What does this partial derivative refer to in this matrix?
So it refers to the one column.
Sorry, refers to the?
It refers to each column, right?
Yes. So this will refer to del f del x1 will refer to the column del f1 del x1 del f 2 del x1 this way till del f m del x1, right? That is a column.
Yes, sir.
Because f was f1, f2, fm, right? So this is a column. This is the first column. So this is the first column, right? Similarly, you will have del f, del xi is that del f1, del x. Sorry, I. So that would be the ith column here. Right? You understand?
Yes, sir.
So the sufficient condition in this case would be that all these partial derivative vectors, these were scalars, right? In this case, they were scalars. In this case, they would be vectors. Which vectors? The column vectors of the gradient matrix, right? I mean, we cannot beforehand say that these are the column vectors of the Jacobian matrix because we haven't started with the assumption that the function is differentiable. That is what we are trying to prove. Unless a function is differentiable at the point P, we don't talk about the gradient matrix, the Jacobian matrix, right? So, back of our mind, we will understand that these vectors, these partial derivatives, are giving me the column vectors of the Jacobian matrix that I am trying to find. Okay? So, what we are saying essentially is, if we have all the column vectors, then we have the Jacobian matrix. You understand? That is what we are saying. If we have all the column vectors exist and are continuous at P, then we have the matrix at P. That is what we are essentially saying. Right?
Yes,
Is
sir.
the last statement clear?
Yes, sir.
we are saying that if the partial derivatives exist and are continuous at the point P, then we have the function differentiable. That means if we have the column vectors exist and are continuous at the point P, then we have the Jacobian matrix at P. That is precisely what we are saying. And the proof, I think, is clear to all of you. Fine? After this, I don't think we have to repeat this proof to you. It's okay? Okay. So now, not much time remaining for today. Just let us quickly see what is meant by the higher order derivatives, higher order partial derivatives. So you see that if I have a function f from Rn to Rm, what is a partial derivative? What is del f? Here f is vector value. I can put a hat here to understand that it is a vector valued function. So if I write del f hat del xi, that means the column vector I'm referring to. Okay? So now you see at the point P, this is a column vector, right? Yes or no? At the point P, this is a column vector
Yes, sir.
because this is nothing but f hat prime at P in the direction EI. What is this? This is an image of the derivative map, right? So this is nothing but f hat prime P, which is acting on EI. Now what is this? This thing is nothing but df hat P, right? This thing is the same as df hat P.
Yes, sir.
So this entire thing is df hat P on acting on EI. And this is a vector in Rm. Rm fp, but forget that. So this is an M vector, right? In some M vector space, Rm, right? So this is the column vector. Now at the point P, this is a column vector. At the point Q, this is another column vector in some other matrix, right? The corresponding Jacobian matrix. Yes or no? Yes? Is it okay? Is it clear to you?
Repeat once.
Sorry?
Repeat once.
Yeah, I'm saying the partial derivative of f hat in the ith direction at the point P is a vector, right? Where does this vector belong to? This is a Rm vector, right?
Yes, sir. Yes, sir.
Right? Fine. Now, can I look at this as a mapping? Say, can I see this as a mapping df del f hat del xi from Rn to Rm again? Can you see this as a mapping which is sending P to del f hat del xi at P? Can I see it this way? Is it all right if I do that?
Yes, sir.
It's right. Okay. So now this is again a function from Rn to Rm, right?
Yes, sir.
For this function, I can consider the jth partial derivative. This was the ith partial derivative of f hat, which gives me a function again from Rn to Rm. So why can't I consider the jth partial derivative of this? I can consider, right? So that would be del del xj of del of this function. Call this function g. Okay, so if you call this function g, which is from Rn to Rm, then that would be del g del xj, okay, at the point P, suppose. What will be that? That will be del xj of the function g, where g is del f hat del xi, okay, at the point P. Is it understandable? We can do that, right?
Yes, sir.
Fine. This I will be denoting by del 2 f hat del xj del xi. I think you are familiar with this notation at the point P again. You are familiar with this notation, right? This is the mixed partial derivative. Fine. This is the mixed partial derivative of a function like f hat. So, in the next class, we will be talking about when to have, when do we have the equality of mixed partial derivatives. I think you have seen this. Have you seen this before, that for a function f, say f is a function of x and y, then del 2f del x del y is equal to del 2f del y del x. Have you seen such statement before?
Yes, sir. In our StatMech course, we have seen this statement before.
Okay.
Yes, sir.
Okay. So this is called, I think, Young's theorem or Schwar's theorem. So I don't know which. Yeah, so I don't exactly remember which who to attribute it to, but this is a statement, and this is true if the function f is a differentiable function, right? Okay. Now we will formally prove this in the next class. When can we say, in a more arbitrary setup? Here you had only two variables and you looked at only the mixed second partial derivative and so on. This can be proved in more generality. What we will be showing is this partial derivative, and by similar means, if we consider this partial derivative, that similarly, following the entire same process, I can come up to del 2f del xi del xj, right, at the point P. I can do similar things to get this, right? So we will be proving that when can we say that these two mixed partial derivatives are same. Okay? Okay?
Yes, sir. Okay.
Okay, so we will stop here today. In the next class, we will continue with the proof of this fact of equality of mixed partial derivatives, and I think maybe in the next class we will be focusing our attention to those two big theorems, inverse function theorem and implicit function theorems. Before that, we will do all this partial and higher order derivatives, mixed partial derivatives and their equalities and so on, maybe the Taylor's theorem, and then we will be looking at inverse function theorem and implicit function theorem. Do you have any question?
No, sir.
Is the proof of the previous fact clear? All clear to you? No obscurity?
Yes, sir. It is
Fine.
clear.
Fine. Okay, then let's stop here today. We will have our next class on Monday and Wednesday as usual. Okay, one thing I need to ask. Maybe again next Wednesday is a little problematic for me. I have something at home. Can we continue with this Friday thing for the next week? Only for the next week. Otherwise, we will be continuing Monday, Wednesdays. Can we take the next week classes on Monday and Friday? Is that fine?
Yes, sir.
Okay. So next week also we will have a class at 4:30 on Friday and 5:30 on Monday. Okay. Thank you.
Sir.